Welcome to EDU AMP. This lesson is all about phase and phase difference. So what I like you to basically be able to do is to find the difference between phase and phase difference, calculate and label diagram the phase difference between two vibrating particles of two different waves, and use the equation for phase difference, and the equation is going to be 2 pi d over lambda. You can get away without using it, but I will show you the equation that you can use. So first of all, I'd like to take you to this nice little bit of software. Now, what you can see here, you can see a traveling wave. Now, a traveling wave, this is a transverse wave. Remember, the wave is transferring energy from the left to the right-hand side, and you can see the particles vibrating vertically up and down here, but the wave is actually traveling from the left to the right. Therefore, it's a classic example of a transverse wave. Now, if you look at the particles going up and down, you can see a red, a light blue, and a yellow ball. And these balls are all different parts of the wave. Now, I'm going to try and show you what is meant by phase difference by trapping it up here. Now, if you look very carefully, and I think I've nearly got it, just missed it off. Get that ball when it's right at the top. Boom, there you go. The red ball here isn't right at the top of the of its cycle, and then the yellow ball is down here. Now, with this here, what we say is these two are out of phase because one's on the top of its cycle and one is out of its cycle. And what you're going to be able to do is work out the phase difference for these two here. Now, to do that is what I'm going to show is what is meant by this phase difference. Now, to go with that then is this bit of software nicely shows you what I mean by this phase difference. So think for now of a particle which can go from the top and then go to the bottom. Now, as this will go up and going down here, and it's actually showing you displacement with time, you've also got a ball going round and round in a circle like this. So what I'm showing you here, this is the particle, any particle on your transverse wave, and what it's doing is moving up and down with time. Okay, and as it moves up and down with time, you've got a traveling wave. Therefore, it is a little bit confusing, but also what we can do is map it to a ball going around and around and around like this. What I mean by here, if it's at this point, it goes to the top, and I'm going to catch it on the top again just here. Oh, just missed it. Anyway, when the top is at that point there, and then when it goes down, it goes to the bottom up. So you can basically map a ball going around and around this circle with this ball going up in here. Now, what we do then is we then say it goes through a cycle. And I'm trying to trap it at the top again, going through here. Just missed it once more. Now, what I'm going to do is introduce another one. I'm going to make it 180 degrees out of phase. Now, trying to get it here. Now, if I make it 180 degrees out of phase, and I'll try and get the red one at the top. No, it's very hard to get on top, to be honest. Trap it. Not nearly. Anyway, when it's at the top, the other one will be at the bottom. We then say they are going to be 180 degrees out of phase. Therefore, one's at the top, one is at the bottom. Now, you need to know all about the different phases going through. So to show you going through here, again, and this is where the mathematics come in, when it's starting at the here, which I'm going to say is going to be that point just there, we're saying the ball is just going to be just here. When it goes to here, the ball is just going to be here. And when it's down here, the ball is there. And when it's going back over here again, the ball is here. So it's going up and down. Now, what I'm going to do is I'm going to put my own axis in, and I'm going to say this point here is at 0 point, where it is going to be up here. Okay, so as it goes round, it's going to 0 degrees. As the ball is going here and the particle goes down there, you've got a 90 degrees phase change. When it goes back over here, then you've got the 180 degrees phase change, and when it goes back over there, then it's going to be 270. Now, we're missing this little bit here. If I continue the line though, going over here like this, when it's back over here, you then got your 360 degrees. You've got a full cycle that goes round. Unfortunately, this picture here starts at that point there. I wanted to start at the top, which is just here. So it's going around a complete full cycle. Now, you also should know we can not only use the units of degrees, we can use something called pi. Now, what I mean by that is 360 degrees is called 2 pi, and you've got pi in your calculator. Therefore, doesn't it make sense here, 180 degrees, you've got pi. Here is going to be 2 pi here, and therefore now I'm going to have 3 halves, therefore you've got 3 pi over 2, which is 270. Add another one, if you go completely around the cycle, this is going to be 2 pi. Hence, what have we got at the bottom here is what I've just done. Here is you've got 0, there you've got pi over 2, here's going to be pi. So as your particle vibrate up and down as well, starting from here, there is going to be pi over 2, here's going to be pi, there's going to be 3 pi over 2, extending my graph over there, that is going to be your 2 pi, and that is going to be a complete cycle. Now, this is why before, when you had the two particles out of phase, one of them was up here and one was out down here, therefore the 180 degrees out of phase. Therefore, going back to my simulation again, to try and show it to you, get it back over here, and making this a bit bigger. As it was going around like this, if I now pause it, I can now introduce a 90 degrees phase shift. Try and get through here, 90 degrees, and there you go. Now, if they're going to be 90 degrees out of phase, then you can see one's going to be here and one's going to be there, and you've got your 90 degrees phase shift coming out. And you can basically, with this software, I can do any phase shift at all. I can make it a 45 degrees phase shift. I'm trying to get hold of that number. There you go. And 45 degrees phase shift is when you're now going to have your pi divided by 4, which is going to give you 45 degrees. So getting back is what we can do now. We can start looking at this wave going through here, and we can start understanding, going back to this simulation, the phase shift between the particles going through. Now, the phase shift coming through here with this software, and I'll start it again, you can see his particles vibrating up and down. Now, they can ask you in examination questions what's going to be the phase shift between the two particles. Now, this one and that one, can you see here, one is up, one is down. That's going to be the 180 degrees out of phase, and then that's going to be all in pi radians. Now, from here to here, that phase shift is going to now be pi or 90 degrees. Now, if you look at this one, between these two particles here, this is where you're going to have a half of 90, about 45 degrees, which is going to be pi over 2. And that's going to be that phase shift just there. So run the software again going forward. The phase shift between the red and the yellow is going to be 180 degrees. And then between the red and the light blue is going to be pi over 2, or it's going to be 45 degrees. Now, if you look very carefully, though, you've got one red ball here, another red ball now. But let these run. You see these two red balls are going to be in phase, because one's at the top, one's at the bottom. Now, they can say now they're either going to be in phase of 0 degrees or 0 pi, or we can say it's 2 pi 360 because it's gone through the complete cycle. So what you can do is use this formula here to actually calculate the phase shift. Now, so to use that formula, the best way I can show you is by using this diagram here. So I've got a particle, which can go through a full cycle going up and down like this. Now, what I'm now is going back to where before you can get phase shift. We said here was going to be naught. Okay, when I go to this point here, I've gone through a complete cycle. So I'm going to say that is going to be 2 pi or 360 degrees. And it's much better to label these. If I go over here, I've got pi, which is going to be 180 degrees. And going back before, what we had is that point there is going to be pi over 2, which is going to be 90 degrees. And also this point over here, then you've got your 3 pi over 2, and that's going to be your 270 degrees. Now, the other way of looking at this, you can look at it in terms of wavelength. And if you go through a complete cycle, here is going to be a wavelength. So what I'm showing you now is the wavelength corresponds to 2 pi. When you've got half a wavelength going over here, then that's going to be your pi. Now the formula shown before was the phase difference is going to be 2 pi d over lambda. Now you can use it, but you can get away without using it by using logical sense. What I mean by that is, if I now go to my red pen, if I start here, I want to find phase difference between that one and that one. I know it's going to be pi. Well, if I look in terms of wavelength going here, that's going to correspond to half a wavelength because a full wavelength is here. Therefore, all you do is bung it into this formula. Therefore, if you've got 2 pi, the difference in terms of wavelength is going to be lambda over 2. But I've also got that lambda over here. So all I'm doing is taking d to be lambda over 2 and putting it into the equation. Hence, 2 cancels with 2, lambda cancels with lambda. The phase difference pops out to be pi. So you can put it into that formula. I can do another one and going to this one here, where I've got this one starting here and want a phase difference to a complete cycle, and that's going to be a complete wavelength. So again, you go back to your 2 pi d over lambda. I'm now going to say d is equal to lambda. Therefore, that's going to be 2 pi lambda over lambda. They cancel out the path difference. So the phase difference is going to be 2 pi. So you can look at it in terms of pi as well, in terms of using a formula and working out using wavelength. Or you can actually look, and a lot of time what I do is sketch this out. I start at 0, go all the way through, and then put the wavelengths in. I then put the phase difference in, and I find that much easier to use. So see, you really have got it, is have a go at these. So what you can have here is you can have a free shot of a wave, traveling wave in time. And it's going through different cycles, but time is going forward down through here. So this one, your O starts in going down, then it comes back up again, and your P is at the top. If we go to a snapshot later on in time, it comes down, then it goes down here, and obviously then come back up again. Q is starting to go up. And what they can do is ask you the phase difference between O and Q. What I do is I go through the whole of the cycle. I've got my 0 here. I know that's going to be pi, and that's going to be 2 pi. Hence, that's going to be pi over 2. And here is going to be 3 pi over 2. So if they ask you the phase difference between O and P, I got O and P here, I can see the phase difference is going to be pi over 2. If they then ask me the phase difference between O and Q, I can see it's going to be complete pi. Again, you can write that 180 degrees. But the phase difference between O and R is going to be 3 pi over 2, and the phase difference between O and S is going to be your 2 pi. And you write those onto the graph, you can see it quite clearly that it changes with time. So what I've been through here, and I hope you now understand, is definition between phase and phase difference. You can basically calculate in a label diagram the phase difference between 2 vibrating particles or 2 different waves, and you can use that equation of 2 pi over lambda. Okay, thank you for now.